Hello everyone, welcome you back for the sessions on the shape memory alloy. In this topic, what we are discussing is with respect to the introduction to the phenomenology, influence of the stress strain characteristics, temperatures, modeling of the shape memory effects, vibration control through the shape memory alloy, design consideration, multiplexing embedded nitinol actuators. So these topics we are discussing in this session. Phase wise, we are discussing all other topics. Now, introduction to the shape memory alloy. As we know that the shape memory alloy possesses an interesting property by which the metal remembers the original shape of and as well as the size and its characteristics transformation temperature, which is known as shape memory effect. In 1962, Destler, a worker in the Naval Ordnance Laboratory who discovered the shape memory effect in the nitinol alloy, which is showing a shape memory effect. The nickel titanium alloy exhibits the greater resistance to the impact in addition to the satisfactory property of the elasticity, malleability, and as well as fatigue, which is known as nitinol. See, the nitinol is one of the worldwide used metal which are having a wide application, especially in the case of the stents. The internal structures are of different at different temperatures. Now, the nitinol has the low temperature phase and as well as a high temperature phase. The unique properties where in the change its phase between the two solid phases involves the rearrangement of the atoms. Especially in the case of the low temperature phase, it is in the martensite form and it is named by Adolf Martens, who is a metallurgist who with a highly twinned crystalline structure. The high temperature phase is nothing but the austenite. This is named by the William C. Austen, which is nothing but a body centered cubic structure. The critical temperature at which the phase transformation takes place are represented as M suffix S, which is nothing but a martensite start, M suffix F, which is nothing but a martensite finish, and A suffix S, which is nothing but a austenite start, and A suffix F, which is nothing but a austenite finish. See, these are all the what we can say the stages which lie in the loading condition with respect to the nitinol, or it may be a shape memory alloy. See, the martensite phase is with respect to the loading condition. The austenite phase is at the thermal stressor, or it may be in the temperature condition, or it may be in the temperature phase. Now, the recovery begins at as and complete at austenite finish. Any method of eating is adequate to change its phase. There is no stress involved in the process as described above, and the deformation mode is non-damping to the crystal structure because of its self-accommodation nature of the deformation. This memory is one-way shape memory alloy and also two-way shape memory alloy. See, the schematic diagram shows the left side graph gives a explanation with respect to the martensite start, martensite finish, austenite start, and as well as austenite finish. See, the martensite start and as well as a martensite finish, it is starting from 0 to 1, and as well as austenite start and as well as the austenite finish is taking place from 1 to 0, where the xi value, which is nothing but the damping value of a material, is varying from 0 to 1. The right side graph gives a explanation with respect to the crystal structure of the shape memory alloy. See, first of all, the shape memory alloy before loading, once if it is at the origin, it will be in the twinned martensite only. Once if the loading starts, automatically it will be in the deformed martensite condition. even after the heating takes place at this particular point also, it will be in the deformed martensite condition only, but the phase change is taking place, or austenite start will also starts at this particular position only. As the temperature rises, automatically the crystalline structure will also starts converting from a deformed martensite, which is nothing but a martensite finished stage, to a austenite start condition. As reaches to a particular point, automatically the austenite finish stage it will be there, which is nothing but something like a square structure. Again the same thing, if it is cool to a room temperature and even below the room temperature, automatically the crystalline structure what we are obtaining is nothing but a twin martensite condition. See, this is a schematic diagram which explain the crystal structure of the shape memory alloy. Now here in the left side graph, which gives the three graphs are drawn with respect to the three parameters. X-axis is with respect to the strain, y-axis is with respect to the stress, and z-axis with respect to the temperature. The ordinary plastic deformation is nothing but with respect to the stress strain curve is only a linear, and as well as the yield point it will be. But in the case of the super elasticity, the entire material it behaves something like a hysteresis. But in the case of the shape memory alloy, it starts from the origin and it reaches to a maximum position, and then once if the material is unloaded, automatically it will reaches to a origin position. But even then also, the some amount of the strain it will be retained in the material. That strain recovery is done by using the temperature range, or it may be by giving a small amount of heat to the metal. The transformation from the martensite finish to the austenite start will takes place. The rise in temperature increases, and also the crystalline structure is changing from austenite start to martensite finish. Once if it reaches to a particular temperature which is around 55 degrees centigrade, the entire austenite start is converted into a austenite finish. Then once if the material starts cooling, automatically the austenite finish will starts converting into a twinned martensite, where the normal where the entire strain what it is being retained in the material is recovered. Especially in the case of the shape memory alloy, below the room temperature we have to cool it. Automatically the entire stresses will be regained, stresses will be removed, and also the strain which has been retained in the material is regained, and the normal material and as well as the shape memory effect will be retained in the metal.